And so it's a pleasure to welcome the first speaker, Martin Elvis, from the Harvard-Smithsonian Center for Astrophysics. And Martin is, in a sense, he's one of the co-organizers of the meeting, of course, but in a sense, Martin was responsible for starting this conversation by an essay he had in Nature. When was that? A couple of years ago? On the possibility that astronomy could get leverage money being, or facilities being produced from mining asteroids to facilitate the next generation of really large space instruments. And so I thought this was a good idea for an RAS discussion meeting. So here we are, and here is Martin's talk. Could we have the lights down a little bit, please? Thanks, Martin.
So I am sort of setting the stage, motivating the astronomers present as to why they should care about the future of commercial space activity, particularly space resources. And let's see. Astronomers are like the great poet Goethe, calling for more light on his deathbed. We will be too, because we always want more light for more. And so we need to look at exoplanets or the most distant galaxies, as they're discussing in the next room. And that means we need bigger telescopes, and that means we're going to get more expensive missions. And as economists say very wisely, if something cannot go on forever, it will stop. And I think we've basically reached that point. We cannot afford anything more expensive than the James Webb Space Telescope. I believe that commercial space, particularly space resources in the longer run, are the way out. I'm not the only one to say this. The PI of the New Horizons mission, Alan Stern, said the similar things a few years ago in Nature. Why do we care? Well, we've got used to being able to make pictures like this. This is the exploding galaxy M82, very nearby. You can see lovely colors, but that's from 3 great observatories. That's Hubble, Spitzer, and Chandra, providing optical, infrared, and X-ray images at high resolution of these, and they're well matched in capability. And it's something accessing the entire spectrum with a rapid feedback is something we've become very used to in astronomy. In fact, we've been doing it for about 35 years. And that capability will soon be lost. That's because these great observatories are old, and worse, in a sense, or better, we're getting a great leap in capability in the infrared from the James Webb Space Telescope in just a couple of years' time, and there is nothing comparable in any of the other bands till at least 2025, probably 2030. Things aren't better in Planetary Science. This is a rather gloomy cover of the decadal review, which the US took in 2011. And they were told to recommend top missions for planetary science. They recommended 3 destinations out of all the places you could go in the solar system: Uranus, Europa, and Mars. And NASA was forced to say, choose one. And that means this simple, tiny list is a 30-year program. That is not really exploring the solar system at scale. That's maintaining your capability, but not really doing a serious exploration. It's cost growth that has cut this so we can only have 1 major mission at a time. If you look at my field of X-ray astronomy, take the leading US missions over the 30-year period, they grew in inflation-corrected dollars at 10% a year compounded. Taking Ian's numbers for the Mars landers, that comes to even faster growth at 15% a year, and as you are aware, the economy only grows at 2 or 3% a year, and that is therefore leading to a collision. It is unsustainable. We're hitting the funding wall. Okay? So much as we may dream of things that are greater, they're not going to happen. This would be an interferometer in orbit that could image continents and oceans on Earth-like planets, exoplanets, and also look up the answers to what a quasar looks like in its interior, but it's not going to happen. We cannot afford anything like that. We have to start planning for the next round of big missions on the 2025 timescale, 2030 timescale even, and we need to be aware of what space technology will be like a decade from now. This has not been an issue in previous 10-year studies because nothing has changed in space technology in 30 years, roughly speaking. But now it's changing. If we don't adapt, the party's over. So this is a series of events that are going to happen over the next 20 or so years in astronomy and planetary science. And you see out to the right where the next flagships are going to be chosen for ESA and for NASA. And we're looking on that timescale. The big thing, of course, is that commercial space will cut mission costs, launch costs. Space can be much cheaper than it is now. The fuel cost is trivial. And if we can cut that cost, we'll get more missions per dollar, and we won't be stuck with just one big flagship. The launch cost savings will affect not only the launch, but also the spacecraft and the science payload. Let's look at where the breakdown of costs is right now. For an astronomy satellite in Earth orbit, it's about 50% spacecraft, 25% launch, and 25% science payload. If you go to the outer planets, you need a bigger rocket to get there in a finite time, and so you need more like 80% launch cost, and because of the tiny payload to total mass ratio of 1.1% for the Pluto mission, and then the rest is 10% each for payload and spacecraft, roughly. So keep that in mind. Now let's compare the timeline for astronomy with the timeline for commercial space activities. And I'll just concentrate on the first part because that's much less unsure and it's also more important to us. So reduced launch costs. This is a case of capitalism working, competition in action. Just the threat of a reusable rocket from SpaceX caused a paradigm shift. Within just a few months before they did that, they achieved that landing. The Airbus said, oh yes, we have a study about this too, and so did United Launch Alliance, and the timing is not accidental, I'm sure. They were stimulated to do this. However, they're not actually going to implement it for too long, and they're likely to be out of business if they don't, I suspect. What will it do for us? Well, the first rocket, reusable Falcon 9, is coming in at 30 to 50% cheaper. That would only save about 13% of an astrophysics mission. That's a modest, useful but modest saving. It doesn't, however, change the game. It immediately changes the game for the outer planets because you're saving half of that 80% launch cost. SpaceX do promise that it will get even cheaper, but that, again, won't be a game changer for astronomy on its own, not even if it was free. You only save 25%. What the big difference is that it will change the way we build spacecraft. Right now, because mass is the most important quantity in designing any space mission, every kilogram, every 100 grams really matters, and that means we have to design Savile Row-style bespoke satellites fitted to the exact mission you want. You can't waste anything. Instead, and so that is a very expensive approach, of course. Instead, once mass is cheap in orbit, we'll be able to use many more robust systems, and we can go into off-the-rack Marks and Spencer type spacecraft and start making them in batches, and the costs will come down. We'll have over-capable spacecraft, which we don't do nowadays, and that will be much cheaper. It's not my idea, it's not a new idea. There was a report in 1990 that said if you can reduce the launch cost by a factor 3, and then you can allow your spacecraft mass to grow 50%, and that alone would bring down the cost of the spacecraft by a factor 3. So that's pretty impressive. But of course the needed cost reduction never came in the 90s, but it is coming now. For the science payload, of course, you may think there's nothing to be gained because we have to have state-of-the-art optics and sensors, and that's true, but those aren't the whole of the payload. There's a lot of other systems that are provided as part of the science payload that can be made cheaper by using more robust components. So let's guess that it's 50% saving there and see what that would do to the overall cost. So in astronomy, Earth orbit, you'd go to roughly half the price. In the outer planets, you'd make somewhat greater savings. It all depends on how much you save on the launch cost in that case. So we could confidently predict that by 2020, a few years from now, we'll be able to afford twice the number of missions that we can afford now, 2 for 1. Now, something else is happening, more remarkable perhaps, on a similar timescale, and that's orbital tourism. There are 2 companies that are going to provide passenger flights to the International Space Station for NASA, and they are also working with companies to provide tourist flights to orbit. Of course, there are 2 more offering cargo trips to the commercial cargo to the space station. 3 suborbital flight companies, Virgin Galactic famously, but also now you've seen Blue Origin do its soft landing, and there's a 3rd company, Xcore, cheap, will probably provide the cheapest ones. 3 of those companies, extra I've noted, are also working on passenger upgrades to orbit. So there could be as many as 5 companies by the early 2020s providing tickets to orbit. That will bring prices down for sure, in the natural way of competition. This is the space resource they're using is not a material one here, of course, it's location. What will that do for astronomy? Well, it'll get us a much quicker instrument testing in orbital conditions, which is the last phase of technical readiness that NASA goes through, and also ESA. And that will mean we can use more advanced instruments. We don't have to wait so long before we can get a good instrument up there, shorter development cycles. It also means that Hubble was famously serviced about 5 times, I think, on orbit by astronauts with the shuttle. And that was technically a terrific success. But economically, it was rather hopeless. It cost you of order $1 billion a time, and so you can't do that very often. But now we're going to be talking about maybe tens of millions for humans to service in low Earth orbit. And again, that means you can risk having more cutting-edge instruments, because if it fails, it's just a nuisance. It doesn't destroy your mission. Here's something even more unlikely, that there will be private research labs in low Earth orbit by around 2020. Bigelow Aerospace is timing their launch of one of these to coincide with the availability of passenger flights to orbit. And their resource that they're selling is microgravity access, milligravity really. They're testing it this year on the space station, so this technology will be very ready by 2020. It's an expandable system. You basically expand this little package on the right, and it grows into the thing on the left, the silvery thing you see, 2 or 3 times in each dimension, so you can get a lot of volume for low mass and low launch cost. It's easy to estimate, because they provided their their price list from Bigelow Aerospace, that by 2020, or 2025 for sure, they could be taking in about $1 billion a year with a space station like this, 2 of their modules. And that's because gene expression has been found to be altered radically, in some cases, in orbit, in milligravity, which is a big surprise to me, but apparently it happens. So it even persists in the progeny back on Earth in 1G. I have no idea why. But biotech companies are a big deal, and they're growing very fast. There'll be a $500 billion industry by 2020. And they're very research aware, very research intensive. They'll really care about this. So if they spend 0.2% of their total revenues on space research, it would not be at all a stretch of the imagination. In fact, it could well be more if it starts paying off. So I think this is very plausible. What would that do for us? Well, nothing much directly, I think, for astronomy or planetary science. This is not a very good platform. You can imagine some specialized uses for like a cosmic ray detector, a gigantic one. But I think the main benefit will be essentially weekly flights, passenger flights to orbit. We're getting to a very high cadence of flights required by this kind of technology. And that will bring costs down, that's another driver to bring costs down. A little further out, there are 2 more steps. Private lunar landers by 2020. That sounds crazy, but in fact it will happen by end of 2017. The Google Lunar X Prize expires at the end of 2017. There are several teams in the running, but 2 have already booked flights. There may be more, but I know of 2. The Israelis and the American company Moon Express. Moon Express wants to sell you a lunar lander. And also China and Japan are getting in on the lunar lander game, so it's becoming a popular spot. Quite rightly, yes? Yes. What will it do for us? Well, I don't think there's anything obvious for astronomy. I'm sure other people are cleverer than me and will think of things, but it's obviously self-evidently good for planetary science, because now we know the moon is a highly non-uniform place. You know it better than me. And we've only sampled 6 randomly chosen spots, not intelligently chosen spots based on knowledge. So we have much to learn, and when we have $50 million at pop landers, we'll be able to have a bunch of them and deploy them at interesting sites. And there will also be some mobility from little rovers or hopping. So that will change lunar science a lot, and of course solar system science as a result. The final step out is asteroid prospecting. At this point, not mining. There are 2 serious mining companies, Planetary Resources and Deep Space Industries. They're testing their interplanetary CubeSats as we speak. The first launch to an asteroid will surely come by 2020. I think they would argue earlier, but let's be conservative. And so they're they'll be having fleets of these prospecting probes by about 2025. Each of these is going to cost about $5, maybe $10 million. It can't cost more because it would ruin their business plan. Maybe they'll go out of business, but maybe not. If they exist, if they work, what will the value be to astronomy and planetary science? Well, with those fleets, we could have some scientifically based ones, not prospecting ones, and we could send out simple instruments. I, of course, want to send out X-ray fluorescence spectrometers, but there are others. And there are nearly 24 different classes of near-Earth asteroid, for instance. If we want to know why, then we have to visit 24 of them. And at the moment, we visit them one at a time at $1 billion a pop. So going at $5 million a pop makes all the difference. You can even get to the Mars system with these. So Phobos, Deimos, Mars orbit in general becomes accessible at low cost. It turns out, by the way, that the miners, the asteroid prospectors, are dependent on astronomers. They need a thermal infrared sky survey for near-Earth asteroids. They need large ground-based telescopes to get spectral types and possibly orbits. You can use X-ray astronomy for 3D navigation to a few kilometers. And of course, astronomy instrumentation is well developed for space, so they need that for their proximity prospecting. This will start a new field, as I mentioned here 3 years ago, called applied astronomy. Okay, so there will be major changes on the timescale that we are needing to plan for astronomy, and in summary, these are the things that we will gain, which are quite different from where we are now. So, temptation. We are not necessarily going to achieve the gains we should from this. It was very hard Googling for a slide on temptation. Don't try it, it's not. It is normal for payloads to grow to fill the budget available, right? So that with the easy answer is to make the one mission you like a bit bigger and use up that savings. It's very easily done. I think that's the wrong answer. The right answer is to grow the number of missions, not only for the spectrum spanning capability that I mentioned at the beginning, but also because a diversity of missions is good for science. It gives you many different approaches and allows less conformity among in the field, among workers in the field, which is a good thing in all of science, and we need to avoid losing that in astronomy. We have it at the moment. Selling multiple missions is hard because a large community gets behind one big mission and then it gets momentum, they speak louder. It's also then hard politically to sell the chosen program to your ministers and Congress or Parliament, because you say, these are the two best things, and it's not as easy a sell as saying this is the best thing, right? So we've got to work on that. We shouldn't be passive about it, we should take up that challenge. Those are 3 slides on the longer term. How am I doing?
5 minutes.
Oh, good. Where things get a little more speculative, but are still within the time scale we should think about. So put these in the it may happen category. There may well be one of these private research labs in a high orbit, perhaps L1, Earth-Moon L1, to get rid of the pesky gravity torques that hit us in low Earth orbit, so we can't get from so we're limited to milli-G, maybe we can get to micro-G with human-tended labs. That implies there'll be a way of getting to high orbit easily. It also requires, not just for humans, but for biotech experiments, that we have radiation shielding. And that requires thousands of tons of material wrapped around one of these labs. That's not going to come from Earth. That would be many billions of dollars or euros or whatever. It's energetically easier to get these supplies from the moon or from near-Earth asteroids. Whether it's cheaper or not, I don't know, but I rather think so once we have commercial incentives at work. What will this do for us? Now we're getting very serious. We're getting into on-orbit assembly of large structures. We can build large dishes, interferometer trusses. We can start to think about building that exoplanet imager that I showed at the beginning. We'll also be able to put our astronomy satellites in the Earth-Moon L2 point and actually service them from there, and that's a better location for astronomy. Even lunar bases, ESA started proposing a lunar base in the 2030s. Jim is going to tell us about mining at the South Pole, which I'm sure he will say will be before 2030, and it may be. But we should certainly think about this possibility. They will be mining water, most likely, for habitats and labs. The place they'll go is at the South Pole, because there you have a continuous source of power near to the valuable resource of water. There's a very small area of these peaks of eternal light which are permanently illuminated, so I think that could be a place of conflict in space coming up. But let's not dwell on that. What's the value of this? Well, now we're getting very big. On-orbit construction with cheap materials, far-side radio telescopes are trivial. Refueling well out of the gravity well will enable large missions to the outer solar system and human missions to Mars. And as Ian has said also, once you have humans there, you get this huge multiplier in efficiency of exploration and research. So this is a terrific gain in the long run. Similarly, the first asteroid mining ventures are likely to start for real in 2030. A lot of the groundwork will have been done. The asteroid redirect mission will give us high-power solar electric propulsion and lots of other valuable experience. And now we're talking about very large masses, cheap resources, very powerful electric propulsion, rapid solar system transit, and very large equipment in high Earth orbits and deep space. So that's a quick run of what might happen in the slightly longer run. Is it all pie in the sky? Well, I might be hopelessly optimistic. Everybody knows that in space, timelines slide to the right very easily, and delays of years are quite common. The savings that I talk about in cost require changing the professional practice of a large bunch of engineers in space engineering, and also involves persuading the space agencies to adopt a different cost model. And that, of course, is it is correct that they should be careful about doing so, because if they make a blunder, they could be in deep trouble. So we have to work on persuading them. It also requires discipline from those choosing the missions to promote for the next 20 years. It requires discipline, and it means from us, from the astronomers, from the planetary scientists, we have to choose missions that allow us to exploit these cost savings. Still, I think it seems very likely that by 2025 all of this will be certainly happening. And in fact, it would be imprudent not to consider these, at least as contingencies, in our planning exercises. And best of all, we should all work to make them happen, or do what we can, because it's the future of the field. There is a great deal to gain if we're able to do this. We can have an endless frontier, an endless future of greater telescopes, greater exploration of the solar system, so long as we bring that cost down and under control. Thank you.
Thank you, Martin. It's an excellent introduction, and Martin has indeed left himself time for some questions.
Wow.
Because we're recording this, your question will be recorded, and also you will need to wait for the microphone, which means I have to get it working. Let's try the other one. Okay, this one's live. Right, sorry, yes, time for questions. Okay, Horace, will you be brief?
I will. Discuss question mark. I'll be very brief. I'd much rather somebody dug up an asteroid than a rainforest for obvious reasons.
Yep.
But there are serious environmental issues with space tourism if it involves substantial hydrocarbon burning. Apart from that, there are issues outside the Earth which could be summarized in a few words. Not only objects, but important locations in space-time, such as Lagrangians. Mm-hmm. And the words which take issues back to ancient Egypt and ancient Greece are ownership, autocracy, oligarchy, and democracy, as they say in exam questions.
Yes.
Discuss.
Certainly. In fact, there's a guy at King's College London, Tony Milligan, who's an ethicist, a philosopher, and I'm working with him on a paper which is basically how much of the solar system should we keep as wilderness, untouched? My answer is 90%, because that's 2 e-folding times, and it sets a tripwire that if we reach 10%, we're remarkably close to 100%. in any exponentiating system like an economy. So that would be my answer. And then, of course, you get into the details of what 10% can you use? Should we be able to put bridges in the Valles Marineris and things like that? Preferably not. But you get into the details. But I think a vast majority of the solar system should be off limits.
Okay, time for one more question. Okay, Mark has a question.
One of the ways we reduce costs at the moment is with international cooperation.
Mm-hmm.
I'm just wondering if you think with the commercialization of this, do you think that will make international cooperation less likely because they'll want to preserve their kind of economic edge?
I don't think that there's a great future in international collaboration in the sense that you gain a factor 2, basically. And that's not enough. If we carry on making the spacecraft the way we do now, the missions we do now, that might buy us one generation, but it isn't an open-ended future. The only open-ended future is to bring the cost down, and basically commercial activity is the only way to bring costs down because the discipline is there. You must make a profit or you're out of business. That does not apply to any space agency.
But they're not mutually exclusive, are they?
No, but it's not an open, indeed.
Are international companies.
Yes.
So. Sorry, I did say, but I'll let James have one quick question.
So just on the cost aspect, one of the reasons that missions cost a lot of money and these cost models are so expensive is the way that risk is shared between agencies and the private sector, in that agencies pay and take all the risk and private sector takes very little. So this can only work if the private sector is prepared to take far more risk and really become commercial, which at the moment it's not in the space.
It is not right now, but I think you'll find that within 5 years it will be dominated by that. So I agree.
Okay, thank you. Can we thank Martin again for a very
stimulating talk.